Today we'll go through three different examples of using the definition of derivative to find the derivative of a function. A formula that will give us the slope of the tangent line. So the first problem that we're going to look at here is f of x. f of x is 3x squared plus 2x plus 1. So our definition says that we're going to take the limit. This would be the average rate of change. And if we take the limit as h goes to 0, this would give us the instantaneous rate of change, or the slope of this would be the slope of the secant, that would be the slope of the tangent. So our derivative, our formula to find the slope of the tangent, would be this limit of this quotient that we have here. So what we can do is we can take out each of the x's here. If I wanted to find f of 7, I'd replace each of the x's with 7s. If I wanted to find f of pi, I'd replace each of the x's with pi's. If I want to find f of x plus h, I'd replace each of the x's with x plus h. So it will be 3 times the quantity x plus h squared, plus 2 times the quantity x plus h, plus 1. And that would give us f of x plus h. So what's in the pink brackets here is f of x plus h. We're going to subtract f of x. That's just what we have right here between my fingers. So if we divide that by h and take the limit as h goes to 0, we have our derivative. The trouble is, if I let h go to 0, we're going to get 0 in the top, we're going to get 0 in the bottom, and 0 over 0 is an indeterminate form. So we're going to expand the top. We're going to expand the x plus h, the quantity squared. When we do that, we'll have what you see here. And then we'll distribute. After we expand the x plus h, square that out, we'll distribute the 3 through the first set of parentheses and the 2 through the second set of parentheses. That'll give you something that looks like what you see here. Now we have a positive and a negative 3x squared. We have a red 2x and a green 2x. We have a red plus 1 and a green minus 1. So these things cancel out, and that leaves us with the expression that you see here. Now the nice thing about this is each of the terms in the numerator now has a factor of h, which we can pull out. We can then cancel that out with the h that's in the denominator, and that will give us 6x plus 3h plus 2. And as we allow h to go to 0 then, this will give us 6x plus 2 for the derivative. So therefore, if you tell me that the function that I'm talking about is this quadratic, 3x squared plus 2x plus 1, this is the formula to get the y values on this curve. The formula to find the slope at any point is given by 6x plus 2. So if I wanted to go back up here, this is roughly what the graph looks like. When x is equal to 0, the y value would equal 3 times 0 plus 2 times 0 plus 1. That'd be 1. And the slope, we said that the slope was given by the formula 6x plus 2. So the 6 times 0 would be 0, plus 2 would be 2. So the equation of this line tangent to the curve at the point 0, 1 would be y minus the y-coordinate we know, equals the slope, and we said that the slope would be 2, times x minus the x-coordinate that we know. And that would be the equation of that tangent line if asked to find it at the point 0, 1. The beauty of this formula is we don't have to just find the derivative at one point, at 0, 1. You can give me any point and we can find the slope at that point. So if I wanted to find the slope over here at x equals, say, negative 5, and then plug y in to find what the y value is there, and plug x in to find what the y value is here. We can plug negative 5 in here and find out what the slope would be at that spot, and then we could write the equation of the tangent line over here. So the derivative gives us the formula for the slope of the tangent line. So our second example of the use of this formula is with this square root equation. G of x is the square root of x plus 1. So I've drawn a graph of this curve here. It looks like no matter where I would put a tangent line along that curve, it's going to have a positive slope. So we don't anticipate getting any negative numbers for this. Again, we'll go back to our definition of the derivative. Again, the first term in the numerator, we're going to replace all the x's in this expression with x plus h's. And we'll subtract g of x. This will give us a formula for the change in y. change in x is h. We're taking the limit as that change in y over change in x as change in x goes to 0. Now, when I look at this thing, if I let h go to 0, I'm going to get the square root of x plus 1 for the red term, square root of x plus 1 for the green, and when I subtract that, it'll be 0. H is going to 0, so I have 0 over 0, an indeterminate form. When we had these square roots that were in indeterminate form, we'd multiply by the conjugate. So I have the conjugate of the square root of the red stuff minus the square root of the green stuff will be the square root of the red plus the square root of the green. Now if I multiply the top of that fraction up here by the conjugate, we need to do the same to the denominator. Because then this stuff that's in this red set of parentheses here, that will equal 1, and multiplying by 1 doesn't change the value of all. But when we do that, we're going to multiply the first two terms together. And so the conjugates, because we're multiplying the first two terms that are exactly the same under the square root together, those square roots will cancel each other out. And we'll just end up with what's underneath the square root for the first term. Now when I multiply the outside terms together, I'm going to get plus the square root of the green junk times the square root of the red junk. And then we'll just get the opposite of that when I multiply these two terms together. So in the end, those two things, this one and this one, they're going to cancel each other out. This and this are opposites. They just cancel each other out. Finally, when we take the negative times the positive, we get a negative, so this is a minus, and the square root of x plus 1 times the square root of x plus 1 will just give us x plus 1 here. So this cleans up fairly nicely. We're going to copy down what we had in the denominator of our conjugate here. So we're going to copy down, we need to have this conjugate thing in the denominator here. And now we'll come down here. Now we can distribute the negative through the two terms in the numerator. We can cancel out the x's. We can cancel out the 1's. And that'll leave us with a factor of h in the numerator, a factor of h in the denominator, and then we have our conjugate in the denominator as well. The h's will cancel out, and now we have an expression where we can allow h to go to 0 without getting 0 over 0. So this will become x plus 0 plus 1, or just x plus 1 under this square root, and the square root of x plus 1 plus the square root of x plus 1 gives us 2 times the square root of x plus 1 in the denominator. So if we wanted to find the derivative of g of x, it would look like this. Notice that this will always produce positive answers, so what we talked about before will be true. The slope of the tangent line will always be positive. In our last example of using the definition of the derivative here, we have 1 over x plus 2. So that's going to be a curve that looks like this with a vertical asymptote at x equals negative 2. Notice that no matter where we put a tangent line along here, it looks like the tangent line will always have a negative slope. So when we're done, let's see if the formula that we get for finding the slope of the tangent line is in fact always negative. So we have p of x plus h minus p of x, that'd be the change in y, over h, that'd be the change in x. Here's, to get p of x plus h then, what we're going to do is take out the x and replace all the x's in the expression with x plus h. So instead of being 1 over x plus 2, it's 1 over x plus h plus 2. We're going to subtract p of x, which is 1 over x plus 2, and we're going to divide that by h. So this is like we did in our previous unit on limits. When we had, if we allow h to go to 0, we're going to get 0 in the top and 0 in the bottom. So we're going to multiply the top and the bottom by the least common denominator here. That will allow these two things that are written in red to cancel out and leave us with a factor of the green x plus 2 for our first term in the numerator. We can cancel out the green x plus 2's in the second term, and that'll leave us with a red factor of x plus h plus 2 in the numerator. So here's just me multiplying those through to both of the terms, canceling out the factors that are like in the numerator, and multiplying the denominator by the same thing. So this quantity that I'm multiplying by is equal to 1, and it's not changing the values at all. Now it's important to remember that this x plus h plus 2 is a quantity, and I need to distribute the negative through the parentheses there. So I'm going to distribute the negative to the x, to the h, and to the 2. And that's important to remember because now when we look at this, we can see that the x's will cancel, and the minus 2 and the plus 2 will cancel, and that will just leave us with a negative 1h, which will cancel out with the factor of h that we have in the denominator. And we can take the limit now as h goes to 0, because we no longer will get 0 over 0. The numerator is negative 1 when we cancel the h out of the numerator. As we let h go to 0 here, the denominator, the first factor in the denominator becomes x plus 2. Second is x plus 2. So we have negative 1 over x plus 2, the quantity squared. No matter what we put in for x, as long as it's not equal to negative 2, we're going to get a negative number out. And that's what we noted about the graph here. We wanted the slope of the tangent line to always be a negative number. Notice also we don't have a slope. It's not differentiable at x equals negative 2 because it's not continuous there. So this is a realistic answer for our derivative. So if the function is 1 over x plus 2, its derivative will be negative 1 over x plus 2, the quantity squared, or the way that we would find the slope of the tangent line. Hope this helps with finding the derivative using the definition of derivative.